Hey there, and welcome to this explainer. Today, we are going to completely unpack the magic behind modern AI search engines and how they somehow manage to comprehend human language. Seriously, if you've ever found yourself wondering how search has evolved from, just blindly matching letters on a screen to actually understanding your underlying intent, you are absolutely in the right place. We're going to look specifically at the architecture of semantic search utilizing dense vectors.
Okay, let's take a quick look at our roadmap for building the semantic search engine. We'll be hitting 5 main points. Number 1, sparse versus dense vectors. 2, the power of transformers. 3, building semantic autocomplete. 4, optimizing for speed. And finally, number 5, bi-encoders and cross-encoders. So we'll start with the real problem behind basic keyword search, move into the tech that powers modern embeddings, see it in action, and then figure out how to scale the whole operation up. Let's get into it.
All right, Section 1, the flaw in keyword search and the vector solution. To really appreciate what AI-powered search brings to the table, we first need to talk about the massive limitation of traditional keyword matching.
Think about it like this. How do machines actually understand meaning, especially across different languages and cultures? If someone types hello to you into a search bar, and a document in our database says Barav Dez in Armenian, how on earth does the machine know those two phrases hold the exact same meaning? Well, a traditional keyword engine just looks at the letters, sees zero overlap, and gives you zero results. It completely fails.
So the answer to our language problem is this brilliant concept called an embedding. An embedding magically encodes human context into math, which allows the machine to actually compute relatedness. It converts words into numerical coordinates in a continuous vector space. Because of this, phrases with similar meanings end up getting clustered right next to each other, totally regardless of how they're spelled or what language they're in. Now look at the stark contrast between the old way and the new way. Over on the left, we've got old-school sparse vectors. This is your traditional inverted index. It's only looking for exact text strings, and the vectors themselves contain mostly zeros. Why? Because they literally have a dimension for every single word in the entire dictionary. On the right, though, we have dense vectors. These are our embeddings. They compress conceptual meaning into abstract features. That means almost every single number in the vector is non-zero and carries really valuable semantic weight. This quote right here perfectly sums up our massive paradigm shift. Our goal is to search on things, not strings. We are moving away from just matching letters on a page to matching real-world concepts and the actual intent behind a search. Moving on to Section 2, the engine, transformers. So now that we know we desperately need these dense embeddings to understand concepts, how do we actually generate them from raw text? Enter transformers. And I'm talking specifically about architectures like BERT and Roberta. You can think of these models as our core translation engines. Here's how it works. First, we take a sentence and pass it through a tokenizer, which chops the text up into smaller word pieces. Then, those tokens are fed right into the transformer encoder. This encoder processes the context of the entire sentence all at once, and it spits out an array of dense vectors that we call a tensor. But here's the really cool part. How does this model actually learn what words mean without humans holding its hand? Well, BERT trains itself using self-supervised learning. It basically plays millions of games of fill-in-the-blank, which is formally called masked language modeling. It randomly hides about 15% of the words in a massive text corpus, and then uses attention mechanisms to guess what those missing words are just based on the surrounding context. By doing this over and over again, it develops a surprisingly deep, nuanced, mathematical representation of human language. Let's jump into Section 3, building semantic autocomplete. We're going to take all this theory and see how we can use these embeddings to build a practical, natural language autocomplete tool. Instead of just clunkily matching letters as a user types, we're taking a much smarter approach here. Step 1. We use a natural language processing library, like Spacey, to extract the core concepts from our document titles, specifically the nouns and verbs, and we just ignore the filler words. Step 2, we run those core concepts through Roberta to get our dense embeddings. Then the magic happens. When a user starts typing, we instantly convert their keystrokes into a query vector, search our index, and return suggestions ranked by their actual concept, not their spelling. The results you get from this are honestly incredible. If you're using an outdoors dataset, a semantic autocomplete can take a partial, unfinished prefix like dehyde, for dehydrated, and it successfully returns related concepts like bag cooking or wag bags. Think about that. Even though the exact letters don't match at all, the engine totally understands the user's outdoor survival intent and guides them right to what they need. Okay, Section 4, the need for speed, also known as optimization. Because when you try to implement this in the real world, you hit a massive roadblock. Comparing a massive 768-dimension vector to every other vector in a giant database is computationally impossible to do at scale.
Seriously, how do we search millions of dense vectors instantly without crashing the entire system or, racking up a cloud computing bill that bankrupts the company? The reality we have to face is that we just can't do exact one-to-one comparisons for everything. We have to trade a tiny bit of perfect accuracy to get a massive boost in speed.
To pull this off, we use something called Approximate Nearest Neighbor Search, or ANN. And the heavy hitter algorithm for this is the Hierarchical Navigable Small World Graph, or HNSW for short. Instead of exhaustively scanning the whole database every time you query, HNSW builds a smart index ahead of time. It clusters similar vectors into these connected neighborhoods. So when you search, the algorithm just hops through these pre-calculated neighborhoods to find the closest matches. It drastically cuts down the number of comparisons the system has to make. Now, alongside HNSW graphs, we have a few other critical optimizations we can use. We can actually shrink the physical size of the vector data using quantization techniques, things like scalar, binary, or product quantization, which basically compress the bit sizes of each feature. We can also use Matryoshka representation learning, or MRL. This is brilliant because it trains models so you can actually truncate the dense vectors, literally chopping off dimensions, while still keeping the core semantic meaning intact. Doing this saves a massive amount of memory.
At the end of the day, our ultimate goal is optimizing for compute performance and keeping costs down. One of the best mathematical shortcuts out there is making sure your vectors are unit normalized when you index them. If you do that, the system can use a really simple dot product calculation at search time. And let me tell you, that is significantly faster and way cheaper to execute than calculating raw cosine similarities from scratch.
Finally, Section 5, the final polish, encoders. So we've just traded away a bit of our accuracy for speed to make vector search viable. The question now is, how do we get that deep, nuanced accuracy back for the final results we actually show the user? The industry standard solution is a two-step pipeline that uses different types of transformer encoders. You see, a bi-encoder generates separate embeddings for the query and the document ahead of time. That makes it incredibly fast, perfect for searching millions of records. But a cross-encoder processes the query and the document together in a shared context. That makes it computationally slow, but highly, highly precise. So what do? We use the fast bi-encoder to grab the top 50 potential matches, and then we pass just those 50 over to the cross-encoder to act like a fine-tooth comb and re-rank them perfectly. And here is the ultimate takeaway for building a world-class AI search engine. You do not have to throw away your old keyword index. It turns out, dense vector search and lexical sparse search are actually totally complementary. If you combine traditional BM25 keyword scoring for those exact matches with dense vector embeddings for the broad conceptual matches, a method known as a hybrid approach, you get the absolute best search relevance possible today. It's really the best of both worlds.
Which leaves us with a pretty fascinating question to ponder. As large language models continue to evolve, as they grow in parameter size and become more and more computationally efficient, will dense vector search eventually become so precise that it makes traditional keyword matching completely obsolete? It is just incredible to watch these models rapidly revolutionize how machines process human knowledge. Anyway, thanks so much for joining me on this explainer, and I really hope you now have a much clearer picture of the architecture powering modern semantic search.